Hello. Today's seminar is Cooperative Groups in CUDA. And on the first slide, I am just going to tell you in a nutshell what this presentation is going to be about. So CUDA before version 9.0 was limited in that it permitted synchronization only within blocks of threads. There was no possibility of synchronization between thread blocks within a single kernel. In CUDA 9.0, a big change was introduced. New functionality was added, which I'm going to be talking about today. And that functionality is cooperative groups. This is a method which permits to overcome this severe restriction of lacking synchronization by organizing groups within groups of threads which can be synchronized in much more final detail than the default synchronization that CUDA provides. In particular, what this means that with cooperative groups, you will be able to synchronize within a block and within sub-blocks of a block. So you can have finer control of synchronization within a block of threads. And also inter-block synchronization is possible. So you can synchronize between subgroups of blocks or even synchronize the entire kernel. And this is really the key thing. That was not possible before CUDA 9.0. So the only way to synchronize the kernel was to basically split it into two separate kernels. Call one and then call another. And this would ensure that synchronization happens in between. And this was possible, but somewhat tedious to do. And the cooperative groups functionality will show you how synchronization is now possible within the kernel. So this talk is about somewhat advanced features of CUDA. So I have to assume that the audience has some previous experience with CUDA and already have used it. So if you haven't, I am sorry about this. But at the same time, I am going to still reference some basic ideas about CUDA here and there, so that if you're not a CUDA expert, you should still be able to get something out of this talk. So let's focus on let me just review some basic idea of CUDA. So CUDA runs on the GPU, and it achieves parallelism by running a large number of threads. In fact, it calls massively multi-threaded functions called kernels. Now, because you have so many threads, they have to be organized, and in particular, they are organized into blocks. And a block can be up to 1024 threads, which seems like a lot, but on the other hand, a typical kernel might have way more threads. So generally, when you're running on the GPU, it is impossible to just use a single block. You have to use many blocks. Now, threads belonging to a given block, they are running together at the same time. They are running on a single multiprocessor within the GPU, if you want to get technical about it. And that means that they can be synchronized. You can tell all these threads to stop at a given line of code, wait until they all reach it, and keep going. But this is not possible between blocks in general. In fact, in general, if you launch a kernel which has a large number of blocks in it, in vanilla CUDA, so to speak, you have no control over the order in which these blocks execute. In particular, you cannot synchronize them. You cannot say all the blocks get to this line of code, stop, and only keep going after you reach this line of code. That is just not possible in vanilla CUDA. And this lack of control, if you will, does impose some cost and restricts the kind of program you can write. In general, CUDA works best if this large number of threads that you are running is completely independent. So let's say you have a loop where every iteration of the loop is independent of the other iterations. In this case, you can have one thread handle one iteration of the loop, and it works pretty well. But then as code becomes more complex, you have to, and there's some dependence between threads, your code has to take care of it. And the one example which I'm going to be using throughout the rest of this seminar to illustrate the ideas of cooperative groups is the reduction example. So reduction just means you have a vector and you want to add all its components and get a sum. So in programming, in your code, that means you have a one-dimensional array, and you want to sum over all the entries and get the sum. So this is a highly dependent, data-dependent operation. If you try to assign a single thread to a single element of this vector, and then have each vector add its value to the overall sum, you will run into what is called the race condition. It is not possible for multiple threads to try to modify the same element of in memory at the same time. You can use various techniques to make sure that they don't do it at the same time, but that means in practice that your code serializes, so the threads cannot run together. The threads have to run one after another, which means that your program would run very slowly if you try to do it this way. However, there are algorithms to compute the sum in a multi-threaded way, and the standard one is called binary reduction, which I'm going to describe in the next few slides. And this binary reduction in particular requires that you synchronize within a block. And because synchronization with vanilla CUDA is only possible within blocks, this introduces some limitations, especially if your vector is large and it doesn't fit within a single block. Which means that generally what you do is first you divide your vector you distribute your vector between blocks of threads. Each block computes a partial sum. And then you have to take these partial sums for each block and do a final summation. And in general, and then you have to get around this problem of having race conditions. So one possibility is to use an atomic operation. Now, an atomic operation means each thread can modify the same element in memory, and the atomic operations ensures that this happens correctly, that data doesn't get corrupted. This means that your code is running slowly, but in our case, since we already did most of this summation for the blocks, and the partial sums which are left, there's relatively few of them, so doing an atomic summation might not be so bad. Another possibility would be to launch another kernel and to do another binary summations on partial sums. So first, I'm going to show you a code for doing the reduction, which just uses vanilla CUDA. So it doesn't use any of the cooperative groups features. And in what follows, I will slowly introduce various cooperative group features which improve the code which I'm showing you. So first, here's the main code. So remember that in CUDA, you run both on the host and the GPU, the device. So the host is the control. That's where you start the code, that's where you allocate memory, that's where you launch kernels, and then the kernels are actually running on the GPU. So in this case, I have my main. I define my n, which will be the length of my vector, which I'm going to be summing. I have an input and output array on the host, and an input and output corresponding arrays on the device. I allocate the input-output arrays on the host here, and I allocate them on the device. So the input array is n times size of float, that's its memory size. The output is only a single number, so it's just a single floating point number for the final answer. Here I initialize my data. In this case, I use random numbers, but I also could have used just ones if I wanted to debug it. And next, I have to transfer my input data to the GPU. So I achieve this with CUDA memcopy. This copies the contents of input host to input device. And then I run reduce, which is a kernel. So I'm going to show you the code for the kernel in the next slide, but this kernel takes the input device array and output device. This will be the output. And here I launch n blocks. That's the number of blocks I'm creating. And block size is the number of threads I have in a block. So after the kernel is done, I do a CUDA memcopy. I copy the data out of the kernel into the host again, and then I just print the result. And finally, I free the memory. So this is just a conventional CUDA main code, and I'm just going to show this to you once just to give you an indication of what this code looks like. But in the slides that follow, I will focus on the kernels, because this is really where the magic happens. So here's my reduce kernel, where the input is the vector x, which I want to sum the entries of, and the output is a single number. So what algorithm will I use? I'm going to use the binary reduction algorithm. And here's a graphical representation of it. So what I will do is each thread will handle initially one element of some temporary array into which I copy the data. So the first step, each thread copies, and to make things simple, I am summing here a vector where all elements are 1. It just makes it easy to follow what's happening. So in the first step, all threads copy 1 into the corresponding entry in the temporary array which holds the data. And the color blue here means that these are the elements which are being modified at this step. Then here, there is a synchronization step. So after all the threads populate this array, 1 entry per thread, there has to be a barrier, because this array has to be completely filled up before we proceed. So here we call a synchronization. In practice, it's a function called sync threads. Once this is done, then in the next step, each thread, half of the threads, so not all threads, so initially all threads fill up this array. In the next step, only half of the threads are involved. And here, as an example, there's a thread which takes this element and this element, so this element, adds them together and stores the result here. And similarly, I haven't shown the arrows because it would be too many arrows, would grow confusing, but the next thread takes this element and this element, adds it together and stores the result here, and so on. Notice that so these elements in blue, these are the elements that are being modified. Each element is modified by only one thread, which means that we don't have any race conditions. There's only one thread modifying each element. And here, again, we have a synchronization step, because we have to be sure that all of these entries have been fully computed before we proceed. And at the next step, we have the number of threads involved. So now there's only 4 threads involved in this picture, and each one takes this. Let's say the initial thread 0, takes this element, adds it together, and populates this element. And then again, we repeat the same process. We have half of the threads involved, and then half of the threads involved. And at the end, the final thread which is left takes these 2 elements and produces the final result. So at the end of the process, this temporary array which we have been using, the first entry holds the answer which we actually want. And then the other entry is called partial answers, which we ignore. So this is how binary reduction works. You can see that in this example, of course, here I'm only showing an array of length 16 because it would be too difficult to draw a longer array. But we can, in our example, we will be using an array of length 1024 in each block. Also, there's a restriction that the size of the vector has to be a power of 2. In the simple case, you can have a general size, but then you have to add some if statements, taking care of the cases where you are out of bounds of the array. So this is a nice algorithm. It works pretty well. It scales logarithmically, but it is limited by the fact that it requires synchronization. And remember that within vanilla CUDA, synchronization is only possible within a single block of threads. So a block of threads can only have at most 1024 threads. So if you're using this algorithm, if your vector was 1024, this would be sufficient. But if it's longer than this, you have to have multiple blocks. And then each block here computes essentially a partial sum. So it only computes part of the answer. And then you have to collect the final result. So let me now show you the code which corresponds exactly to the algorithm which I have just described. So here's the code for the kernel. So I have my kernel. So here's a keyword global, means it's a kernel. It's called reduce. It takes as input the vector, and it takes as output the single element, which is the answer. Here I declare a shared space. So this will be the temporary space which I will be using. And this is shared memory is a special region of memory which only exists for the block of threads. So each block of threads has access to this region of memory. And the size of this will be block size, which will be 1024 in this case. Then remember, this is a kernel, so this code is launched by every single thread which I have created. So it's the number of blocks times the block size. So here, each thread computes the element I of the vector it is responsible for, and it calls a sum called reduction sum block, which uses the temporary space and the element of the input array which the thread is responsible for, the element I. And then here's our function, reduction sum block. So it takes as argument this shared space, and val is the value that it has to add. So here we have, so here in these lines we have the algorithm which the previous picture described. So we have a for loop. So in the first part of the for loop, each thread populates the temporary space, and then it does the addition. So first there's the population step. So the values are populated. Then there's a synchronization step, and then each thread takes its value and a value sort of shifted by I, and so it does the summation for that particular step, and then there's a synchronization step again. So again, this picture is reproduced here. And at the end of this, each thread has a value, but only the thread with index 0 has the actual true value for the partial sum of the block. So at the end, after I called my kernel, each thread has some number block sum, but only thread with thread index within the block 0 has the true partial sum. So the final step is I need to add these numbers together, and here I use a function atomic add. So this means that for each block, so we have all the blocks. In each block, there's a thread which has ID 0, only one thread per block, and this thread will run this line of code where it takes its partial sum and it atomically adds it to the output value. And so here we have many threads will be running this line. So multiple threads will be taking their block sum and adding it to the output. But the reason this doesn't result in any race conditions is we have the atomic add functions. If we just tried to add this to the output without the atomic add function, we would get the wrong answer because we would have race conditions and our value would be corrupted. Okay, so far, this is vanilla CUDA not using any cooperative groups. So, and also it uses the atomic add, which isn't optimal because this is an operation which serializes. Only one thread can be performing the atomic add at a time, which can slow you down because it's not happening in parallel. So the question is, how can we improve our code and how can we get rid of this atomic add and have an efficient binary summation for the partial sums? But a binary summation which doesn't launch a second kernel. So we could launch a second kernel to get these partial sums added up, but that will result in a more complex code. So let's improve our codes, and we are going to be using cooperative groups and the associated objects for this improvement. So the heart of cooperative groups is it introduces new objects which can represent groups of threads. In particular, there's a new data type called thread block. So this is a data type which describes a group of threads within the block. This can be the entire block or some subset of threads within the block. And similarly, there's a data type called grid group. So this describes a grid of blocks, either the entire grid, meaning all the blocks involved in the kernel, or a subset. Now, to make this work in your code, you have to include add an include file, cooperative groups _groups.h, and you have to be using a namespace for cooperative groups. And also in practice, when you're compiling the code, you have to provide some flags. Especially, you have to select the architecture which supports cooperative groups, otherwise your code will not compile. And there's also some flags which are necessary. So another thing to mention is that your GPU has to be recent enough to support this kind of thing. So if your GPU is really old, and these days it would mean it would have to be really old, like Kepler generation or something, it might not support it. So once we have these new groups describing, new objects describing groups of threads, how do you initialize them? Well, you start from existing groups of threads. So there's a function called this thread block, which will initialize your thread block group that you're creating and make it just the existing block. So with this function, you create an object G, which contains all the objects within the blocks of threads that the thread is in, right? And similarly, there's this grid function, which creates a grid group object, which just holds all the blocks within your kernel. And now you can create new groups by subdividing these groups through a process called tiling. So for example, you can take a block of 1024 threads, create a group out of that, and then tile this group into new groups of 32 threads each, right? And we will see how it works in subsequent slides. And once you have these cooperative group objects, you have functions associated with them. For example, there's a size function, which will tell you how many threads there are in the object you created. You have the thread rank function. This tells you that for a given thread that belongs to an object, what is its index within the object. And finally, we have the sync function. This means synchronization within the object. So you can imagine this whole approach just vastly extends the kind of synchronization you could do in CUDA before this, which was really quite limited. You could only synchronize within the block, and you only had the sync threads function, which synchronized within a single block. That was all you can do. So now you're extending this to basically being able to synchronize within a general subblock or within a general subset of blocks. Okay, so what I'm going to do next is I'm just going to take my reduction function from before, and I am going to rewrite it using these cooperative groups objects. And the essence of this rewriting here is the resulting function doesn't have to run on the whole block now. It could actually run on a subset of a block. So what do I do? So here's my kernel. It's largely unchanged from before, except that here I define a thread group G, which will correspond to this thread block. So G means the block that the thread is in. And then I call a new function called reduction sum block, which has an additional argument. So here I'm actually passing the object. I'm passing the block. But other than that, things are unchanged. So reduction sum block runs. Each thread computes block sum, and then thread with ID 0 has the partial answer, which is then atomically added. And what happens inside the reduction function, the reduction sum block? Well, I am passing the thread group. And notice here that the ID of the thread is computed from the thread rank method of the group. And also the synchronization doesn't happen with sync threads. It happens with the sync method of the thread group. So far we have just renamed things. Basically, instead of using sync threads, I'm using the .sync methods. This hasn't changed otherwise. But the main thing here is that this function is now capable of synchronizing not necessarily over the entire block, but it's going to synchronize over whatever group of threads you pass it to. So this function has become much more general. There's also an interesting code safety feature by introducing this, because if your code grows more complex, you might write a device function which has a synchronization, but you might forget that synchronization is there, right? And synchronization, according to the CUDA programming guide, can only work, like sync threads only works if every single thread in the block runs that line. If if you forget this and you don't have every single thread run sync threads, you might either get a deadlock or undefined behavior. So this is something that you have to be careful about. So in a sense, this function makes it explicit that a group of threads is being passed, so there's an implication that some kind of synchronization is being done on this group of threads. So this results in a kind of a cleaner, better controlled code than the sync threads method, which could sort of hide synchronizations on you. All right, so at this point, I have just rewritten my code to use cooperative groups. It's a little bit cleaner, but we really haven't changed anything. We are still using atomic summation. So the next step is, how can we get away from using atomic summation, atomic add, but still have just a single kernel? For this, we need synchronization. So my goal here is to replace atomic add with a single thread addition. A single thread will just add out all these values. But in order for that to work, I have to be sure that all the blocks have finished computing before I run this single thread to add the values. So I need some kind of a kernel synchronization step. So that's what I'm going to be talking about next. So synchronization within kernels is a harder proposition, because basically in CUDA, a block already synchronizes. So if you are adding finer details to synchronizing a block, that is relatively simple to do. But in a kernel, it's different, because in a typical CUDA kernel, you have possibly a lot of blocks, and they can't all be resident on the GPU at the same time. Basically, GPU does a kind of queuing where it takes a block, computes it, so it loads a block, computes, it offloads, loads a block, computes, and offloads. How do you synchronize this? I mean, it's an impossible task. So CUDA solves this problem by basically requiring that a kernel that you are synchronizing has to be resident on the GPU in its entirety. So the kernel has to be loaded, all the blocks of the kernel have to be loaded up onto the GPU before you can synchronize. This imposes pretty severe restrictions on how big your kernel can be. So on your GPU, there are hardware limits on how many blocks can be resident at the same time, how many threads can be resident at the same time. It is a kind of actually a complex calculation, and there's even a spreadsheet called occupancy calculator where you can compute these numbers. But in a nutshell, if you want to simplify it, essentially, if your blocks are 1024 threads, then 1024 threads is the limit on how many threads can be resident on the multiprocessor of a GPU at the same time. And so this means that only one block of 1024 threads can be resident, and a GPU has, let's say a Volta P100 GPU has 56 multiprocessors. This means that on a Volta GPU, you could have a cooperative kernel, which at maximum would have 56,000 threads. And for some problems, this will be allowed. For some other problems, it will not be. So for some problems, cooperative kernels will be possible, and for some, not. So it is you can see that it is a kind of a restrictive method which will not work for every single problem. There's also the difficulty that different GPUs have different number of multiprocessors. Let's say a high-end Volta will have 56 multiprocessors, but a consumer card, a cheaper consumer card, will have much fewer. And now your code here is dependent on how many multiprocessors you have. And in fact, I haven't included these steps, but if you are using cooperative kernels, you probably need to add to your code some lines which actually query how many multiprocessors you have and determine how many blocks you can have in your cooperative kernel. And the final thing is when you launch a cooperative kernel, the syntax for launch changes a little bit. Specifically, you write your kernel as you did before, but to launch it, you have a function called CUDA launch cooperative kernel, the first argument of which is the kernel itself, a pointer to the kernel, and then number of blocks, block size, and then finally kernel arguments. And kernel arguments cannot be supplied directly. You actually have to create an array of pointers to the arguments and pass that. So it is a little bit annoying, but that's required. So this is basically the price you pay for synchronizing across a kernel. So there are some difficulties. It's not cheap. So it won't work for every single calculation you want to do. But on the other hand, you do gain quite a bit of power, and for certain codes, this kind of synchronization will be highly beneficial. So it's definitely good that CUDA added this functionality. So let me show you then how do I run this code now that a barrier is possible. So in my code, I launch my kernel like this now as a cooperative kernel, and I have a relatively small vector, so I fit within the size limitations. And now, how does my kernel change? So the input is still the same. Now there's also one more array I am passing. It's the array to store the partial sums. So each block will compute a partial sum, and now I want to store that somewhere because I'm not running atomic add anymore, so I need to store it. So there's one more array to store. And now within my code, I create a grid group object, which just stores the current grid of blocks. So I use this grid method. Once I did this, now it is possible to run grid.sync. And this line, grid.sync, means that as the code runs, all the blocks have to stop at this line and wait until every single other block has reached this line before proceeding. So in this case, each thread launches the reduction sum block function. This is the same function I had before. It stores so it takes the blocks, so then the thread 0 within each block, which has the full partial sum. It stores it in this new array called partial underscore sum. Here there's a synchronization, so this ensures that this array is fully populated before we proceed. And then finally, I have only one thread just loop over this array and compute the final sum. So you can see here that I have replaced the atomic add, which I had before, with just a loop performed by a single thread. And this loop is possible because I have a synchronization step added here. So this is not amazing code. I have replaced an atomic sum with a loop, which actually will not really result in any improvement in speed. It might actually run a little bit slower. But this just sort of demonstrates the point that synchronization is possible, and now I can compute the full reduction within a single kernel without having to break up the kernels into two separate kernels, which gives me a somewhat simpler code. But I want to do even better than this. So I would like to do a binary reduction on the partial sum. So again, now in my case, I have only 32 blocks. So this is only an array of 32 elements, right? So I should, if I wanted to do a partial sum with this function, if I want to do a reduction on this array of 32 elements with this function, I would need a block of size 32, right, for a conventional function to work. But my block, when I launched my calculation, the block size is 1024. So how do I get a smaller block effectively, a smaller group of threads? Where this is where the final step comes in, and this is the tiling step. So once I have created my group of threads, whether this is, let's focus on a group of threads within the block. I can then subdivide this group of threads into tiles. So if I create a group G, which contains all the threads in the block, and this group is created by using the thisThreadBlock method, I can then call a tiled partition method, which takes this group and it subdivides it into tiles of 32 threads each. So now there's a new thread group called tile32. And now we can use this new thread group to synchronize across. And this process can be repeated. So I could take tile32 and I could call tiled partition with tile32 as an argument. And I could, for example, take tile32 and divide it into groups of 8 or 4, whatever. So even finer subdivision is possible. So so this is how this method works. So you can imagine that this is called by each thread in a block, and then each thread now has access to a group thread object which only groups together some smaller subset of groups within the block. Okay, so here's the final slide. So this will show how it is possible to do two binary reductions in a single kernel. So here I have my grid. So the first half of this up to here is the same as in the previous slide. So the grid, the threads in each block, they compute the partial sum. This partial sum is stored in a partial sum array. Here we synchronize. And now I want to do a binary reduction on this partial sum array. So the first thing I do is I create a tile partition where out of my entire block, I now make subgroups of tile 32, each one of which contains only 32 threads, right? And then I want only one of these tiles to actually do the sum on the partial sum array. In particular, what I'm going to do is I will only have tiles in block 0, and within this block, I mean threads within block 0, and within this block only threads which have ID less than 32. So I want only the first 32 threads in block 0 to do this sum. So then I called reduction sum block. Notice that this is the same function I called here, even though the same function actually runs on a different number of threads. Because here I was passing G, so I was passing the entire block of threads. Here I am only passing a tile, a group of threads with only 32 tiles, 32 threads in them. But the function still works, even though I am passing a small group of threads. And remember that the essence of this function is that it can synchronize, right? And here, by using a tile, I'm going to be synchronizing across a group of only 32 threads. Not the entire block, but only a group of 32 threads. So you have to really imagine just how much flexibility and power this kind of synchronization possibility gives you, because you can now have really a fine, detailed level of control over small subgroups within your block. And the final step is, after all of these after this total sum have computed, I now have one thread take the result and write it into the output array. So I know that when I do this partial sum, only thread 0 within that ran this has the final result. So then only the thread in block 0 and with ID 0 writes the output of the final sum. So I hope we are nearing the end of this talk. So I hope that you see how cooperative groups can give you much more power to control the synchronization of your threads. And here with the final slide, this is just kind of a generic slide which illustrates that you can synchronize threads at an arbitrary level of complexity, really. So here in this example, we have some initial block of threads, let's say, and here you can tile partition these blocks into two groups, each one of which contains half of the threads. And this is the time axis here, so this shows the time, if you will. And then you can run synchronization on one of these subgroups and not on the other. So you can improve parallelism. Basically, these threads can be running while these are synchronizing. Then you can tile partition again, so you can take this subgroup and partition it in even finer detail. You can take this partition it in even different kind of detail, so it doesn't have to be the same all the way across. And then you can synchronize on only some of these and not the other ones. So the way to think about this, before cooperative groups, if you wanted to have any kind of synchronization, if this was your block, this red line would have to extend across the entire block, because sync threads has to be called and has to work across all the threads in the block. So this kind of, you can see that this kind of parallel overlap, where this function is, this half of the block is synchronizing while this is running, this would not have been possible with just sync threads. So your code will be missing some opportunities for parallelism and it will be running much more slowly. Whereas with this approach, you can really maximize the parallelism that you can get. And here I will stop and take any questions you might have.